Let me start the recording. Okay, welcome. My name is Bill Goble. Today we'll be talking about meeting architecture constraints in SIF design and verification. I have a lot of experience in engineering, and I've spent about the last 25 years studying field failure data. As part of that work, I spent a lot of time studying all the problems and all the benefits of field failure data, and to a great extent, that's what we're going to be talking about today. I work for exida. Exida is a global corporation with offices around the world. We are composed of a group of people who not only have product development experience, so many of our people thoroughly understand what's inside all the sets of equipment that you have. We have people with safety certification experience, and we have a lot of people with application systems level design and operational experience. exida spends a lot of its time in industries that value reliability and functional safety. I spend most of my time in the automation and process industries. Many of our other people spend time in automotive and semiconductor and actually several other industries. exida does systems level consulting. We have a significant product certification and professional certification group. exida does a lot of training, and we supply engineering tools and reference materials. And it might seem like a lot of diverse activities, but all of our activities are oriented toward functional safety, reliability, and cybersecurity. I'm proud to say that exida has many of the world's top experts in functional safety, cybersecurity, and reliability. We have authored most of the industry references for automation, safety, and reliability. We have published industry data handbooks for component data and equipment data, and we've authored some of the most comprehensive books on functional safety in the market. I did get a comment, I'm not getting audio. Yeah, but if you're not getting audio, you won't hear me. I assume everybody else is getting audio. Just to make certain, could someone type me a message? And if you're getting the audio, please. Let me just double check. Yeah, lots of messages. Audio, okay. All right. Well, yeah, lots of messages. Good, thank you. Not everybody is okay, but you'll have to do the best on your end, because for most people it's working perfectly. Let me just clear out. Okay, we cleared out the question bar. Let me check status. I do see there's a few people that don't have audio. But we need to proceed. I think everything from this end looks excellent. Today we're going to be talking about safety instrumented function verification. But I'd like to start by just reminding everyone of the fundamental concepts in IEC61508. There is a defined safety life cycle. It's a detailed engineering process, often considered important to deal with software reliability. And the second fundamental concept is a probabilistic performance-based design, often thought to deal with hardware reliability. But the fact is, we want protection against systematic failures or systematic faults, primarily design mistakes, because such things can cause dangerous failures. We also want protection against random hardware failures. And in the world of 61511 and in the world of 61508, both of these are meant to be are protected against if you follow all the requirements of these standards. Any safety instrumented function design is possible, as is there's no cookbook in IEC 61511 or 61508. You come up with your own design, and then you perform a verification function to see if your design meets the requirements of the standard. Now, what is this verification function? Well, there are three, what I call design barriers. Three things that you must check to see if a design meets a particular SIL level. First of all, you need to check systematic capability. This is a measure of design quality. In the world of 61511, you can either purchase a product that is 61508 certified, or you can do your own prior use justification. Second thing you have to do is a probability of failure on demand calculation, if it's a low demand application, or a PFH calculation if it's a high or continuous demand application. Last, you must check what are known as architecture constraints. Architecture constraints. Perhaps you've never heard of the word, but it means minimum levels of redundancy in a design. A lot of people, and the bottom line here is really simple, you do not meet all the requirements of functional safety standards unless all three of these barriers are successful. You can't go down the road unless you've jumped all three hurdles. But today we're going to be focused on architecture constraints. The first question everyone asks is, well, why do we even have architecture constraints? I've heard impassioned arguments that they are of zero value. If you're doing a probability of failure on demand calculation and the probability numbers say that you meet a SIL level, why do I need architecture constraints? The reason that many of the members of the committee wanted to also require architecture constraints are listed on this screen. I've heard equally passionate arguments that failure rate data is no good. And what if somebody uses very low failure rate data? We have to have design rules. We really need a cookbook. We have to have design rules for safety. Just checking, I thought I saw a question come up, but the screen is blank. Okay, it's gone. Lastly, many people think the whole probabilistic concept is not sufficient to ensure safety. Now, why would anyone ever think failure rate data was no good? I was reading a paper one weekend, and I saw this cartoon. I had spent several days in the previous week studying a set of field failure data. And as I read this cartoon, I thought to myself, that's how they do their field failure data. Essentially, there's two steps in the process. Number one, type random numbers into a spreadsheet. And number two, you're all done. Well, it's no wonder that people doubt reliability data when, in fact, maybe some people seem to act this way. Now, that is just a cartoon, but nevertheless, there is some questionable data out there. And when people use very optimistic data and calculate a PFD average, I see questions coming up on the status screen, but the screen is still blank. So please try typing your questions again, and I'll do my best to answer if they come up on the screen. Let me just double check again, because I most certainly do not want to miss questions. Oh, there they go. Some good questions and comments. Why don't we use hardware fault tolerance and keep it simple? Well, I'll explain that today. But the primary answer is you increase the false trip rate. And false trip rate is a very bad thing. All right, that was pretty much it. I lost audio. Did others? Let me check my status screen. This indicates audio is working just fine, being transmitted. Sorry if you're having trouble. A few more comments. Good, good. I'll deal with those as we proceed. Thanks very much for all your questions and comments. This audio approach, this textual approach is very useful. Now let's get back to the presentation. If someone enters extremely optimistic data and does a PFD calculation, you might show, like this example from the Excellentia software from Exida, that the design meets SIL 2. If all you do is a PFD calculation and you're using extremely optimistic data, and I have seen such data, you might be very much misleading yourself. The same exact example, when using more realistic data, shows that the design only meets SIL 1. Over and over again, at least every month, when I audit PFD calculations, I see people using extremely optimistic data. And of course, that's exactly why the committee wanted to imply or require minimum levels of redundancy. Optimistic data is not safe. It's like a ticking time bomb. You are not meeting your tolerable risk criteria. And because there were some incentives to use optimistic data, some members of the committee felt very strongly that architecture constraints must be imposed. How do we deal with these architecture constraints? Well, fortunately, there's a number of optional ways to show compliance. In 61511, architecture constraint tables are simplified versions of 61508, tables which were created before 61511 existed. However, there is a clause in 61511 which allows users to use the 61508 charts if they wish. And there's a clause in 61511 that says if you have prior use data, you can reduce the architecture requirements by 1. 61508 has two specific charts called Route 1H. One is for Type A, simple components, and a second chart, which is one level higher for redundancy, is for Type B, complex components. And 61508 also offers another alternative called Route 2H if data quality can be shown. So we have several different options to meet architecture compliance. Now, 61508 and 61511 define a metric called safe failure fraction. You can see by looking at this metric that products that have inherently fail safely will get a higher number because of the lambda SD and the lambda SU. And DD will give you a higher number because, in fact, it's a matter of diagnostic. There was a comment. I saw a draft of the new 61511. It appears transmitters are now considered Type A devices. Do you consider transmitters always fail in a deterministic manner? Oh, no. Definitely not. Do you know that transmitters have multitasking operating systems and 16 and 32-bit processors, multiple processors? The transmitters that we are certifying at exida today are more complex than the logic solvers we used to certify when we started the company back in the late 90s. Yeah, I think that deserves a million comments. Transmitters are not type A if they have complex circuitry. Good comment, thanks. All right, let's keep going. A high number is good, 100% is good. A low number, like less than 60%, is not so good. This is a metric that is independent of total failure rate because it's a ratio of failure rates. And it was developed primarily in the context of complicated microcomputer-based safety devices. We take this metric, safe failure fraction, and in the 61511 chart for logic solvers, you can see that there is minimum levels of hardware fault tolerance, minimum levels of redundancy, as a function of SIL level. If a complex device with a safe failure fraction of less than 60 is going to meet SIL 3, we have to have, oh my, minimum hardware fault tolerance of 3. What's hardware fault tolerance? Well, a 0 means you have a single channel of equipment. A 1 means you have 2 sets of equipment. A 2 means you have 3 sets of equipment. And a 3 means we have 4 sets of equipment. How'd you like to see 4 PLCs wired together? Oh my. This can be a real way to increase the false trip rate of any design. 61511 has the second chart is for field equipment, and they simplified. It's identical to 61508 if you assume safe failure fraction is 60 to 90 for type B components and 0 to 60 for type A components. And there was a time back in the 1980s, 1990s when this is probably a good assumption. 61511 prior use clause says we can reduce the levels of redundancy by 1 level if we have good field failure rate data. So basically we have 3 charts, 3 different ways. Most people, however, will probably just switch over to the 61508 tables. That's what I do. For type A, there's a chart that shows you safe failure fraction, SIL levels, and hardware fault tolerance. If I have a type A element, it's less than 60%. Single channel is only good for SIL 1. Just checking status screens again. Everything looks all right. And type B is an order of magnitude tougher, or in general requires 1 higher level of redundancy. Now, both of these tables I showed you are the Route 1H. Is there any problems with architecture constraints? Oh, another question popped up. If you need additional instruments to meet the hardware fault tolerance, for example, additional primary elements. I'm not sure what primary elements are, but hardware fault tolerance means you need extra sets of equipment for safety purposes. Are there any problems with this architecture constraint requirement? We looked at why they're there. Just check another comment. Oh, there are additional requirements if you want to claim prior use. Yeah, there's a lot of them. But we have a whole web seminar on exactly how to claim prior use. Stay tuned. Take a look for it. It's a good web seminar. Are there any issues with architecture constraints? Well, they have caused some problems. Artificial redundancy requirements do exist when short proof test intervals are valid. Once we were verifying a batch process where there was a full set of tests automatically performed at the beginning of each batch. The batch ran each day. So in fact, the mission time was 1 day, worst case. In such a situation, the probability of failure on demand during that mission time is a very small number. And they really get a very strong risk reduction factor. But architecture constraints require redundancy. That means higher false trip rates with no impact on safety. And that's not a good design. I've seen artificial redundancy requirements when simple devices are combined with type B devices. If I combine a type A and a type B, which you really do if you have this if you have multiple element or multiple components, devices in one element. For example, a design uses a certified pressure transmitter with a safe failure fraction of 93. Well, that's pretty good. That means you can use one transmitter in a SIL 2. But if you add a remote seal, the safe failure fraction dropped below 90%. That means you've got to use 2 sets of equipment. And in fact, when you do the PFD calculation, you show you have a strong margin for a single set of equipment in SIL 2. But the architecture constraint forces us to put in redundant equipment, leading to higher false trip rates with no significant improvement in safety. So we have some issues. And I think those issues are the result of a major debate within the different committees, certainly major debates that I heard. And in the 61508 committee, the Route 2H solution was included in the standard. And that involves reducing architecture constraints if you have a high confidence in the quality of your failure data. Remember, though, that high confidence is more than just statistical analysis. It's more than just confidence interval in a statistical calculation. A high-quality data collection system is required. The applications and environmental conditions must be similar. And these are important attributes of having good, high-quality data, which allows the PFD average calculation to be valid. You can read the words of 61508. Some of them are on this particular slide. The words that pop out to me include field, feedback for equipment in similar applications and environments. There are published standards on how data must be collected. There is an amount of field feedback, but what it says here is think about how much data you have. But it never said, by the way, how much data you need. Another question. What generic data sources can be considered high quality? I will have a discussion on that later. In my opinion right now, I'll hold that for later. Yes, hold on, Keith. We're going to answer that in a bit. Expert judgment is required. Experts at exida have been studying field failure data for 20 years or more. We've seen a lot of Dilbert cartoon data. And to a certain extent, you have to be very careful about such data. Now, that may very well make it impractical for individual end-user companies to ever use Route 2H because the amount of field failure data and the expertise required to evaluate the data. But nevertheless, Route 2H has been somewhat well-defined here. If we take a look at the field data collection standards cited, and we've read through them quite a bit, the ISO and the IEC standards have some pretty basic requirements for what data must be collected. Of course, data must be collected from similar applications and similar environments. A certain amount of minimum information must be collected, including the application and the environment, as found conditions for a proof test. And there's a long list of things that are really important, some of which are listed in these standards and some of which are not. Another question came up. Thank you so much for all the questions. Does the data have to be from a specific end user or from the collective experience of a manufacturer? Well, the fact is the standard does not say. As a reliability engineer for the last 25 years, it's my interpretation that any data that is valid from field operation in a similar environment and in a similar application can be collectively gathered and used. And that's exactly what we do at exida. I'm going to tell you about it. There is a good standard from Germany, the Numor NE93, which is very similar but somewhat more detailed than the ISO IEC standards. And it is absolutely my impression that the AICHE, the Chemical Engineers Center for Chemical Process Safety, PERD, the Process Equipment Reliability Database Committee, has done the best job of all. They have defined data that needs to be collected. They have defined failure modes of all kinds of process industry equipment, and they've set up a database to collect and verify quality data. So there's some good efforts out there. exida has been heavily involved in the PERD database initiative, and we've made sure that our SILSTAT data collection software is compatible with PERD. But the fact, and everyone believes that field failure data is the ultimate source of good information, it's a rich opportunity to obtain failure rate and failure mode. However, a lot of the data sources do not have enough information. And that's okay. Even limited information is quite useful. The manufacturer's warranty studies are also useful, especially for failure modes and detailed root cause analysis, but they're not that useful for absolute failure rates, primarily because many manufacturers don't understand the application, they don't know the application, and manufacturers have no idea the real number of operational hours in the field. And most importantly, manufacturers don't really know how many of the failed units are returned. I guarantee you, all failed units are not returned to a manufacturer under warranty. The surveys that exida has done indicates that it's a function of warranty period, cost of an instrument, and particular application parameters. Now, 61508 did a pretty good job of characterizing the attributes of Route 2H, but what's not there? I'd like to point out that there was no indication of the total number of hours required, nor was there any indication of a minimum time period required. So anyone that's going to implement a program really needs to define those for themselves. If you extract, you can create a table showing the architecture requirements of Route 2H. Although there is no specific table in the standard, the requirements are in the language, in the words. But there are some things that are important. There is no safe failure fraction calculation. Like 61511, it's identical to Type B components with safe failure fraction of 90 to 99, and Type A with safe failure fraction of 60 to 90. And interestingly enough, this table is identical to the table in 61511 if you have justified prior use or proven in use for devices. So I don't find this table to be new. It's just a reiteration of the old 61511 table from 2003. Take a look at it. You can see same numbers for SIL 1, 2, and 3. 61511 does have some special requirements and refer you back to 61508 for SIL 4, but for the most part, those of us in the process industries don't see SIL 4. So what is a reasonable Route 2H set of criteria? At exida, we have adopted the criteria of 1 billion unit operating hours of collective data per product type. Now, 61508 does not give you a number, as I said earlier. So at exida, we wanted to pick a number that offered such overwhelming evidence that it really could not be argued. 1 billion unit operating hours is a lot of field failure data. And you might think, are you guys crazy? Nobody will ever get 1 billion unit operating hours. Well, in fact, yeah, we can get it. I'll talk a little more about that later. You can't just guess at the field failure hours. You have documented, traceable field failure studies. We also imposed a rule. Now, this is not in the standard, but for exida, we won't judge data to be Route 2H until field operation has gone 1 year or longer. And we require that an FMEDA be done with Route 2H compliant components. We think it's a pretty strict interpretation of the standard and hopefully somewhat conservative. Now, I know some of you are thinking, whoa, what's that last one? What is an FMEDA? Well, using a component database, a design is analyzed one part at a time. We look at every integrated circuit. We look at every resistor. We look at every capacitor and look at every failure mode of these components and ask the question, how does this impact the safety function of the device? It's an extremely detailed and systematic procedure, but allows one to predict product failure rates, product failure modes, and diagnostic coverage, even on brand new designs. And we think it's far more accurate than any manufacturer's field failure data. And few people would argue that one. But what's the problem? There is a big negative. The accuracy of the FMEDA depends on the accuracy of the component database, because it's garbage in, garbage out. The component database has to include all the failure modes as a function of different environmental conditions. Failure rates definitely vary as a function of stress, environmental conditions, and application. So a component database has to deal with all of those variables. That's why it's essential that a component database must be based upon and calibrated by good field failure data. If one does an FMEDA analysis of a product and gets the total failure rate of that product, it's absolutely possible, and in my mind essential, that the FMEDA results are compared at the product level to field failure data. That comparison is the basis of any good calibration and verification scheme. If there are differences, they must be explained. Perhaps the field failure data uses a different definition of failure. Perhaps the field failure data collection process has some weakness. Or perhaps there are missing components or missing failure modes in the component database. But whatever the problem, any differences must be explained and corrected. At exida, after 10 years, we've done hundreds of field failure study comparisons using both end-user and manufacturer data sets that represent a total of over 60 billion unit operating hours. And in many cases over the years, we have updated and calibrated the component failure database to provide relatively accurate results for one of 7 operating profiles, including subsea, offshore topside, process industry field conditions, process industry control room conditions, and we even have things like automotive and things that aren't process industry. At this point, I believe exida has more failure rate data than anyone in the world. The other thing we can do to verify is check. There was a comment, that means that most of these studies do not meet the 1 billion hour requirement you just stated. Well, no. 60 billion hours were in the data, and in fact, given 60 billion hours of data, most of the components at this point do meet the 1 billion hour requirement. Now, no one wants to propose changes, and many people challenge the 2H because they're worried it would decrease safety. In order to check this, in order to check the value of architecture constraints, exida did a study of over 50,000 safety function designs. These were designs from many of our customers around the world. They're all anonymous, but the designs were sent to exida. Just raw data. Here's the design, here's the sensor configurations, here's the components we used, here are the numbers we used, and here are the results. Interestingly enough, 70% of the time, the SIL level was limited equally by the architecture constraint and the PFD average calculation. So 70% of the time, these two barriers gave us the same SIL limitation. Another comment came in. Thank you. You guys are doing a great job. Are the failure rates published in the SERH, leveraging the collection of data that you are describing? Answer, yes. Can others access the data in any way? The SERH database is published in book form, it's published in electronic form, and the SERH database is built into the Excellentia software. So that data can be accessed in 3 different ways. Thanks for asking. I'll explain a little more about that later. Another question came up. You guys are doing a great job. Thank you. In the pie chart, is SIL AC based on 1H or 2H? Oh, good question. I should have done a better job on the slides. It's 1H. It's absolutely the old 1H requirement. Thanks for asking. Now, this shows that 70% of the time, the 1H architecture constraints did not limit the sill level any more than the PFD calculation. That was good. That's real good. We also discovered that 95% of the time, of the 50,000, people used the SERH failure data, which results from the exida FMEDA analysis. Approximately 5% of the safety function designs used my own failure rate data entered by the engineer. Now, we also found that 15% of the time, the PFD average was the limiting factor, and the architecture constraint did not improve safety. But, and this is the group that counts the most, in 15% of the cases, the architecture constraint limited the sill level, even though the PFD said you could go to a higher sill. So for 15% of the cases, the architecture constraint seemed to improve safety. So we dug in. In that 15% group, we found that 10% of the time, there were very short proof test intervals. Now, if those proof test intervals are realistic, and we cannot judge that, but if they're realistic, in fact, the higher sill level dictated by the PFD calculation was absolutely valid. And the architecture constraint really did nothing more than increase the false trip rate. So for that case, I'm not confident that architecture constraints were valuable. However, in 5% of the cases, the my own failure rate data allowed the PFD calculation to go much higher than architecture constraints. And that's exactly what many of the committee members were worried about. People were using very low data. Now, where would someone get very low data? Well, in fact, some certifications are done based on failure data derived from cycle testing. This failure rate data comes in between 100 and 400 times lower than typical exida FMEDA data. And there's nothing wrong with cycle test data, except that it refers to applications where the equipment is dynamic, constantly moving, at least 10 times per year. It does not refer to your typical process industry low demand, where a product will not move for maybe a year or 10 years. And there are engineers who use this cycle test data, I hope unknowingly, and come up with PFD numbers that are just wildly optimistic. How do you compare failure rate data to FMEDAs? In this case, we got data from a refinery. You can see that an analog transmitter was judged to be roughly 3 times e to the minus 6 total failure rate. In this study, which was basically from the 1980s and 70s, 8 times 10 to the minus 6 for microprocessor-based equipment. A Dow study done more recently said basically 5 times 10 to the minus 7 for a pressure transmitter. Now that study did not indicate whether the transmitter included, whether the number included pressure, manifolds or impulse lines or remote seals, because that level of information just was not present. In the IREDA database, they publish a dangerous failure rate of 3 times 10 to the minus 7. We can use this data to compare to FMEDA results. The first one we looked at, for example, was an analog pressure transmitter. It's a type A device. It had basically 4 times 10 to the minus 7 and another analog pressure transmitter design that was a bit more complex, which had 8 times 10 to the minus 7. Those two numbers matched the Dow data pretty closely. It's even pretty close to the ORITA data, since these products don't have any automatic diagnostics. The dangerous failure rate is the dangerous undetected failure rate. Not bad. In several FMEDAs of more recent designs, the numbers seem to be coming between 5 and 6 times e to the minus 7, which is kind of a bit more conservative than the Dow plant study data. But of course, these FMEDAs were done without any remote seals. And some of these numbers are coming up in the range of ORITA. But ORITA does not state whether a pressure transmitter data includes impulse lines or manifolds or remote seals either. An FMEDA of a transmitter, including a remote seal, came at 7 times 10 to the minus 7, which is a bit higher than the Dow data. And the dangerous undetected failure rate is close, or getting closer to the ORITA database. Now, at exida, we were able to go to Norway last year and did detailed comparisons of ORITA with FMEDA results. And ORITA does include site-specific maintenance-induced failures, which FMEDAs do not. And so I found that in those detailed comparisons done in Norway, the FMEDA data came in very close to the field failure data collected by the ORITA folks. Another question or comment. Good. Is ORITA data static or updated to include new devices? I don't know this for sure, but in my discussions with when I was up in Norway, it was my impression that they were updated to include new devices. The issue is that they categorize in a very general way. Pressure transmitter. They don't distinguish between the various designs. They don't distinguish between safety-certified products and older products. And I think that level of detail is important. Take a look at the dangerous undetected failure rates in this chart. The lowest one are the certified pressure transmitters. 2.8, 3.7 times 10 to the minus 8. Now, why is that? That's because automatic diagnostics detect many of these failures and send the current to an out-of-range signal. I saw no indication that the ORITA data had any information about whether failures were detected or not. At exida, the SERH failure data is based on FMEDA results calibrated with nearly 60 billion unit operating hours of field data. When Route 2H criteria is met for a component, it is now marked as 2H in the SERH database. When all the components in a particular design are categorized as 2H, the product is then marked 2H. We've done 2 years of significant research, and the component database verification is now complete with most components, but not all, showing more than 1 billion unit operating hours. All products that have only 2H components can be 2H qualified in the SERH database. They have to ask, well, geez, does that mean Route 2H applies to everything? And the answer is no, it cannot. And I don't see how it could ever apply to new technologies. Why? We don't have 1 billion unit operating hours, or in some cases even 1 million. I can think of dual-core microprocessors and sub-micron designs of these latest new technologies. 2H cannot really apply to new and unique designs because they're using new components. And There are many products with components that are just not in high volume production for a sufficient time period. So it's absolutely true that Route 1H will be used on many devices. And in the exida SERH database, we will be marking, with the next release, we will mark those components where we have documented and traceable evidence of Route 2H compliance. If you do have this, you can, instead of the Route 1H table, where, for example, if I have a SIL2 design and I have a pressure transmitter in combination with a remote seal, which is one element, and the safe failure fraction drops below 90, a single channel is only good for SIL1. Even if that transmitter by itself has a 93% safe failure fraction and excellent onboard certified automatic diagnostics. We can now use the 2H table, so we don't need redundancy for SIL2. That's a good idea if it reduces the false trip rate and does not impact safety. One of the reasons I'm pretty comfortable with it, and many of us here at Exida are, is because it's really exactly the same as the 61511 tables in 2003, where if you had prior use justification, you could use the same table for SIL 1, 2, and 3. Now, if anybody has any questions or comments, please let me know. I'd like to thank you again for the many comments that we've had during this presentation. If you have any others, please consider typing them up right now, and I can give you some answers. I will also say that if something comes to your mind later, tomorrow or next week, go ahead, send an email. I will type in my email address, and we will deal with it asynchronously. Okay, a comment. So, is 2H basically certified, proven in use? Well, 2H is not the same as product certification. So I'll change it. So the question as stated is no, it's not the same thing. But is Route 2H the same as prior use or proven in use? And to a great extent, these are the same concepts. Route 2H in 61508 has done a much better job of defining the parameters. Route 2H is somewhat more restrictive and more detailed than the prior use statements in 61511. So in that regard, it's good. But as one comment made earlier, yes, there is fundamentally a big difference. There are other statements in 61511 about quantity of data and manufacturers' quality system audits and so forth, which makes the 61511 criteria stronger than the 61508 Route 2H. So the bottom line is the combination of these. A certified device, a 61508 certified device with Route 2H data behind it is probably the best you can get. It gives you the best of both worlds. Full confidence based on history of field failure data and certified design processes to protect against systematic integrity. So I like to think that many of the certified products that are coming out that have both 61508 certification and Route 2H compliance are really presenting a set of evidence that's stronger than any other, that they are suitable for safety. All right, I see our time is about up. but I don't want to end too quickly. Any other questions or comments? Please type in your questions. For those of you who are up late at night, thank you very much for attending, and thank you all for a set of very good questions and comments. This will be recorded, and you can review a full set of slides later. I don't see any other questions now, so let me just say thank you very much. If you find these web seminars of value, please look at the exida schedule to see all the new stuff that's coming. So I thank you very much, and hold it, one more question. Oh, just a thank you. Oh, you're welcome. Thank you for attending. We'll see you next time. Bye-bye.